This video gives a short review of using Laplace transforms. We're going to review the properties of Laplace transforms needed to solve problems in viscoelasticity. Should note it, we are not deriving these from Laplace integrals in this video or in this class. This is covered in prerequisites to this class, and we're only using the properties that have been then previously established. So you should not have to take the time during these to solve Laplace integrals. So using Laplace transform to solve linear systems, keep in mind this can only be applied to linear differential equations because the Laplace transforms, the properties we derive are only true when the equation is linear. So to know that it's linear, all the terms have to have one dependent variable or its derivative. It's all fine to multiply terms by cofactors, that is parameters. Also, a term can be nonlinear with respect to the independent variable, usually time, certainly in these models we're solving here. And in fact, we call this possibly nonlinear function of time a pushing function or an input function. An example of a linear system is the Voigt model with the pushing function being sinusoidal stress, which we see here. That is a amplitude sigma naught times sine omega t. That's the sinusoid, and the step function here means this is 0 before t equals 0. So, and we see this is linear because we have this term only has one variable. This has just the derivative of a variable, and this one has no variables except time. This is just the pushing function over here. Keep in mind, this is just a constant. That's not a variable. It's not a function of time. So we can use these Laplace transforms to solve linear differential equations by transforming the ODE so it becomes an algebraic equation, and then solving the output in the Laplace domain, which is algebraic manipulation, and then take an inverse transform to get the output in the time domain. Reminder then of the details of this. The definition of a Laplace transform is that we often use the capital letter that corresponded to a letter. So if this is a function y of t, we'll let y, capital Y of s, equal the Laplace of y of t. And it's defined as the integral from 0 to infinity of y of t times e to the minus st dt. So we know t is in time of second. S here is in the inverse time, and you can see the units by how that comes in over here. From this definition, the following properties are derived. And again, you don't want to be deriving these when you need them. You should simply memorize them. The first critical property is that Laplace transforms are linear. That is, the Laplace of a constant times a function is the constant times that Laplace of the function, and Laplace of two different functions, the sum of two different functions, is the sum of the Laplace of the two functions. Another critical property is that the derivatives in the Laplace domain turn into polynomials in S. So the Laplace of a first derivative is S times the Laplace of the function minus its initial condition. To help you remember this, you can remember that S is an inverse time, and so multiplying by S is like taking the derivative with respect to time. This is a useful property because it converts a differential equation in the time domain to a polynomial in S in the Laplace domain, which means instead of solving a differential equation, we only have to solve an algebraic equation. The last useful property of Laplace transforms for solving engineering problems is that we can use time shifts to turn signals on and off. So this is, we say, the Laplace of y at t minus a times the step function of t minus a. And remember, a step function steps from 0 to 1 at times t equals 0. And so this is stepping when t minus a equals 0, which means it steps at time a up to that. And so this allows you to switch and add a function that simply steps on at time A, or you can take the negative of that in order to make one that was already on turn off. So you can turn one on and then turn it back off by subtracting the same function in a time-shifted manner. So common transform pairs that are useful in solving viscoelastic problems are that the Laplace of the delta function is just one. Recall a delta function has integrates to 1, it occurs at 0, and it's infinitely high. It's infinitely high and infinitely narrow. Laplace of this phi, this is the step function, is what we had just said. That's the step function from 0 to 1 at t equals 0, and Laplace of that is just 1 over s. The Laplace of t times the step function, what that means is that we have something that is increasing at time after times t equals 0, but the step function means it's 0 below times t equals 0. And if you want to increase at a velocity, you just put the velocity in there. And then Laplace of a exponential function, again, starting at time 0 equals 0 and then decaying. So this is t equals 0. It was 0 before then. And if it's e to the minus at, that means its characteristic time where it decays e-fold occurs at 1 over a. And so the Laplace of that is 1 over a plus s. Similarly, Laplace of the 1 minus this. So 1 minus this is something which at t equals 0 starts to increase. And it approaches the value 1. Sorry, that also started like 1. So at t equals 0, it goes from 0 up to starts approaching 1, again with this critical time constant 1 over a. And you can see this by plugging in. If you plug in t as 0, you get 1 minus 1 here. That gave you the 0. If you plug in t as infinity, you get 1 minus 0, which means you keep the 1. So finally, Laplace of a sinusoid, and the Laplace transform of that was a over s times s plus a. The Laplace of a sinusoid, again, that means we until t equals 0, it's 0. That's why the step function is there. And then it starts oscillating. So Laplace of that is a over a squared plus s squared. So these are transforms that are useful. They're here, and you'll always want to make sure you use a lookup table unless you memorize them. So a little bit more on the time-shifting property of Laplace transforms. So recall we said the time shifts allow you to turn signals on or off, and so we have this function here that defines how we switch a time shift in the time domain to express it in the Laplace domain. So we'll show two examples. If we turn constant stress on at t equals 0 and then off at t equals t naught, and we'll have the constant stress be of magnitude sigma naught. That's just a parameter that indicates what we're holding the stress to while it's on. And so that means that we've done this at 0, at t, right? This is this, and then we go up to sigma naught. And this is in a stress time axis. So we just turn the signal on and off. Excuse me, that should be a t, not a tau. So we turn it on with y1 of t is equal to sigma naught times the step function. That just says we step up. Instead of us stepping up by 1, we step up by sigma naught. We then turn it off by adding a y2 that's the negative of the step function. So if we had said that step function was just saying it would have gone 0 until this point and then going down there. And when we added that to what we already had for the first one, we add those two together, we get the line in blue that gives you the actual response. So combining these then, so the total pushing function sigma is the sum of the turning off and turning off signals, which is simply this. And then if we took the Laplace transform of that, we would have this equation that we're operating on in our Laplace domain. Our second example is that we're interested in increasing stress linearly till T equals capital T and then decreasing linearly. This is what we're looking for then is we have 0 and then we start up and then we go back down. So this is T equals 0, this is T equals capital T. So this is a hysteresis response. This is a type of hysteresis, except here we are controlling stress instead of strain and seeing the response in strain. So here we turn this on with a function that's a velocity v naught times t times the step function. That means it's 0 until t equals 0, and then it increases at a velocity into infinity time. We now need to turn it off. So we want it 0 until time t equals capital T, so we don't interfere with what's before. And now we want to not just turn it off, which would be subtracting the velocity v. We want to make it reverse directions, and we still have the function going up, so we actually have to go down at twice the velocity. So that explains the minus 2v naught. We want this to start at time capital T, so we have the step function t minus capital T. And then finally, we want to multiply by t minus capital T because we just want to jump this. We don't want to make a big jump. We just want to start turning it down. If we had that times the little t, we would already be multiplying and be way down as though we would jump to as though we had been doing this from the beginning. So now we add these two together, and this is the equation that we get. Finally, to take the Laplace transform of this hysteresis function, we will remember that the Laplace transform of a linear function of 1 over s squared. So the first term converts the v naught times the linear increase in velocity v naught to v naught over s squared. The second term converts the minus 2v naught velocity to minus 2e to the negative capital Ts times that v naught over s squared because of the equation up here for the pushing function. And notice here how exactly this matches where both the function and the step function are of t minus a, and we see this here. So these examples illustrate how to use the time-shifting property to both design functions in the time domain and take the Laplace transform of them later, and can also be used as you recognize these terms to take an inverse transform and interpret it in the time domain.